Well, chapter 15 is about solutions. And we're not going to cover all of this. We're going to talk about solubility, ideas of solution composition, and then we're going to talk about concentration. The unit we'll use is molarity. And the rest of the chapter we're going to skip because it's not in the course outline. So what is a solution? Some of the words that we use in chemistry have different meanings than the same word that we use in everyday life. In real life, a solution is more likely an answer to a problem. In chemistry, a solution is a homogeneous mixture. It needs to be homogeneous. Remember what that means? What does the prefix homo mean? The same. So homogeneous is the same throughout. Can you give me an example of a homogeneous mixture? Gasoline, yeah. Because gasoline contains a lot of different hydrocarbon compounds. There's octane and nonane and all kinds of other stuff. But it's uniformly mixed. What's the opposite of a homogeneous solution? A heterogeneous. Now, a heterogeneous is not a solution. It's just a heterogeneous mixture. And that would be something like salt and sand, or oil and water, or something like that. It's going to have at least two different sections. So in this homogeneous mixture, we have at least two components, the solvent and the solute. And there can be more than one. There's only one solvent, and the easiest way to define that is it's the substance present in largest amount. So whatever thing there's more of, we consider that to be the solvent. Usually. And then the solutes are the other things. In this class, we'll mostly talk about aqueous solutions, and the word aqueous refers to dissolved in water. So in an aqueous solution, water is the solvent. So Kool-Aid is an aqueous solution. It's got red dye number, well, if it's cherry Kool-Aid, it's got red dye number 40, and it's got sugar, and it's got flavor, but all those things are the solutes, and they're dissolved in water, because there's more water there than anything else. Here are some examples of different types of solutions. We often think of a solution as being solids dissolved in water, and down here we have a couple examples like that. Seawater. What's the difference between seawater and fresh water? There's all the salt dissolved in it, right? So seawater is in the liquid state. The original state of the solute, though, the salts that are in it, are solids. If they're pure by themselves, they're solids. That's why, you can go to the store and you can buy sea salt. It's salt taken out of seawater and purified. And the state of the solvent is a liquid. The solvent there is water. A sugar solution, such as Kool-Aid, or maybe you put some sugar in some tea, or you made coffee. Similar idea, the original state of the solute is a solid and it's dissolved in a liquid. But we can also have gases dissolved in gases. The air in this room is a homogeneous mixture. It's a solution. What would we say the solvent is? It's the gas that there's more of. Okay? And then the other gases are dissolved in it. We can have two liquids mixed together. Vodka and water. Okay? Alcohol is a liquid and water is a liquid, and when you mix them together, they mix up just fine, and you have a solution of alcohol in water. Antifreeze in water is another example of a liquid-liquid. We can also have solutions that are solids. Brass. Brass looks like an element. You think of a brass doorknob. It's a metal, but it's not on the periodic table, is it? There's copper and lead and some other familiar metals. Brass is a solution of different metals. It's a mixture, a homogeneous mixture of different metals. And so you can have solids dissolved in solids. Obviously, you can't just take two solid metals and put them together and have them mix. You need to heat them up and melt them and mix them in the melted state and then let them cool down, and then they'll be thoroughly mixed. We can also dissolve gases in liquids. Carbonated beverages are an example of this, where you have carbon dioxide, which is a gas, dissolved in water. You can even have gases dissolved in solids. So pretty much any combination of the three physical states of matter is possible for solutions. So let's look at ionic substances and how they dissolve in water. I'm thinking there's something missing here. Yep, there it is. So sodium chloride, table salt, beaker of water. These are things that we're familiar with. If we put salt into water and stir it up, it dissolves, right? It all mixes together and we have a homogeneous mixture, a solution of sodium chloride in water. The sodium chloride is the solute and the water is the solvent. So what happens with ionic substances is when they dissolve, they break up into individual cations and anions. You see here in this illustration, we've got the cations, the sodium ions, and the chloride ions, and they separate, and that's how they dissolve in water. They can do this because the water molecules are polar. So here we have our little Mickey Mouse heads. And we've talked about water and how it's a polar molecule and how the oxygen end has a partial negative charge. The positive end has a partial the hydrogen end has a partial positive charge. Of course the positive end is positive. The positive end of a water molecule is attracted to the negative chloride ion. Now this has a full -1 charge, and this water molecule only has a partial charge. But if we get several of these around, like over here, if we get several water molecules around, the water molecules interacting with the chloride are going to replace the interactions that this chloride ion had with its neighboring sodium ions. So they come around and they make it feel comfortable. So, we can kind of extrapolate this to social situations. If you go with maybe 3 of your best friends to some big, college gathering or something where you don't know anybody, you're probably going to stay close to the friends you came with, right? Because you know them and you feel comfortable with them. But what if these other people are really friendly and they come up and they say, "Hi, how are you? I'm so-and-so. Let me show you over here." And a bunch of people come around and are just making you feel comfortable, and they're making your friends feel comfortable too. You're much more likely to go off with these new people, right, and explore, right? And so that's how I think of ionic compounds dissolving in water. These water molecules are attracted to this negative ion. They come around, they make it feel comfortable, and so it can go off and float around in the water. Now, if the water couldn't also do that with the cation, we'd have a problem, because we couldn't have just the sodium cations left over here. But water also has a negative end. And so the negative oxygen end is attracted to the cations and will surround the cation and also make it feel comfortable. And so this is how ionic compounds dissolve in water. Ionic compounds do not dissolve in solvents that are not polar, because they don't know how to interact with each other. They need this polarity, this negative and positive end, in order to surround them and make them feel comfortable. More scientifically, we have to replace these interactions between the sodium ions and the chloride ions. That interaction has to be replaced. We can't just rip it apart and not replace it with anything. That's an energetically unfavorable situation. And so that wouldn't cause the ionic compound to dissolve. Any questions? Now, other things that are not ionic also dissolve in water. We mentioned vodka in water, or alcohol. This is ethanol, which is the alcohol that we can drink in moderation without killing ourselves. The other alcohols are really, really bad. But alcohol, ethanol, mixes with water very nicely. It's not an ionic compound, but it is a polar molecule. It has this oxygen over here. When we look at its structure, we see, yeah, that looks kind of lopsided. Here we have this oxygen, and here we have an oxygen-hydrogen bond. So what kind of intermolecular forces could we have? ET, phone home. The hydrogen bonding, right? We can get hydrogen bonding here because we have an HO bond in a polar molecule. So this ethanol molecule has this very polar bond here, and the water molecule has similar polar bonds, and so these two can interact with each other. And so this ethanol molecule can go into the water and they can mix, because you know, kind of think of it as speaking the same language. They both speak polar language, right? So my husband's Japanese, I'm Swedish, and so I will pick on those two ethnicities because then I can't be accused of being politically incorrect. So imagine you have a big room and you've got a bunch of Japanese people who oddly enough only speak Japanese, and a bunch of Swedish people who only speak Swedish. Which that would be hard to find because in those countries most of those people also speak English, but we're going to pretend that none of them speak English. Are you going to see a lot of mingling and interacting between the Japanese and the Swedish? No. They can't communicate very well. They're going to be playing charades with each other, right? That's just hard. Have you ever tried to communicate with someone that you don't share a language with? It's really tough. But if they have a common language, now we say, oh, okay, yeah, actually you're allowed to speak English now, and they all know English, then they're going to mix and intermingle because they can communicate with each other. And so this ethanol molecule and the water molecule, because they're both polar, they essentially speak the same language. It's the language of interaction between opposite charges. And the same goes for those ionic compounds, that they understand this interaction between positive and negative, and so they can mingle and mix up together. Sugar. Does sugar dissolve in water? Yeah, it dissolves very nicely. It's very soluble. This is a sugar molecule. This is a sucrose molecule. It's kind of big and complicated, isn't it? Do you see any polar bonds in this guy? Remember, for hydrogen bonding, we were looking for F, O, or N bonded to hydrogen. That's why I said ET, phone home. Are there any OH bonds here? There's a whole bunch of them, right? There's little OH bonds hanging off all over the place. Those are polar bonds that are capable of hydrogen bonding, and those are going to interact very well with water molecules. They speak the same language, and so sugar is very soluble in water. Not all substances are soluble in water. Let's look at oil and water. We know from experience that those don't mix. Oil is a nonpolar molecule. There's lots of different oils, but basically they end up looking a lot like this. They're just carbons and hydrogens, and they're very symmetrical. Most of them are actually very, very long. But you've got a really long molecule like this that's just got carbons and hydrogens. Does that look like it would interact very well with water? I'm just going to go on and on and on off the screen. Do you see anything lopsided in that that would suggest that the molecule is polar, that it's got one end that's different from another? It's pretty uniform, isn't it? There's no oxygen, nitrogen, fluorine bonded to hydrogen. Carbon is over here. It's not nearly as electronegative as those other ones. So these bonds are slightly polar, but because the molecule is so symmetrical, the whole molecule itself is nonpolar. It doesn't have a positive end and a negative end. So here we've got the oil up here. In order for it to mix with the water, it has to be able to interact with the water. Remember we talked about the different types of intermolecular forces, and we talked about the London forces and the dipole-dipole forces and the hydrogen bonds, right? And which did we say was strongest? The hydrogen bonds. So water, what am I pointing at? Water has hydrogen bonds because it's got that hydrogen-oxygen bond and it's a polar molecule. Water also has dipole-dipole forces and the London dispersion forces because everything has London dispersion forces. Dipole-dipole forces were between polar molecules, and the London dispersion forces are something that everything has. But these are the weakest. This non-polar molecule, is it going to have dipole-dipole interactions? No, there's no dipole. All it has are London forces. So its interactions are very weak, and the interactions between the water molecules are very strong. So the oil essentially cannot get into the water because in order to get in, it has to break these interactions between the water molecules. You could think of water as a really tight-knit group of people. These people, you know, they've gone to school since they were in kindergarten, they live in the same neighborhood, their lives are enmeshed with each other. And here we have oil coming in who doesn't even speak the same language, never met these people before, and he's trying to break in and become part of their social circle. Is that going to work out very well? No, it isn't. The oil cannot interact with the water molecules. The water molecules are interacting very strongly with them. So essentially the water molecules are excluding the oil. They're pushing it out. There was a great illustration in another textbook, and I really should pull that picture in here, but I haven't done that yet, so I'll have to make up a picture. So imagine that these are marbles. Okay, we've got blue marbles, and those are just regular glass marbles, and then we'll have red marbles, and the red marbles are magnetic. What's going to happen when you mix these marbles, where you've got regular glass marbles, which really don't interact with each other, do they? They just bounce off of each other. And you've got magnetic marbles. What do magnetic things do? They stick together. So you take this group of marbles, glass marbles and magnetic marbles, and you mix them up, and what's going to happen? The magnetic marbles are all going to stick together in a clump, aren't they? That's what's happening with the water. There are strong attractions between the water molecules, and so they are going to stick together. The oil has very weak interactions between other oil molecules and very little interaction with the water, and so it basically gets excluded. So what's going to happen when we mix up those marbles is that all the magnetic marbles are going to clump together, and they're going to exclude. Does that make any sense? Really need to get rid of these illustrations, the animations. So, in order for a substance to dissolve in water, we basically need to make a hole in the water structure for that solute particle to get in. And when we do that, we're breaking some of the interactions between the individual water molecules, and those need to be replaced by an interaction between the water and the solute. Now when we had an ionic compound, so here's what, oops, forgot what I was writing with. So here's water. And water can interact with the sodium ion because there's a partial negative here. So ions can dissolve in water because there is this force of attraction between the charges that replaces the broken hydrogen bonds. And polar substances like alcohol can also dissolve because they speak the same language. They also have the dipole-dipole forces and or the hydrogen bonding, and so they can replace those interactions that were broken by pushing into the water. But the nonpolar substances like oil cannot. They can't get in there because if you break the hydrogen bonding that water has with itself, you have to replace that with a similar interaction, and oil can't do that. So we have this kind of generalized saying that helps us to understand solubility. Like dissolves like. So on a very general level, there were exceptions to this, of course, but on a very general level, if the two compounds are alike in terms of their polarity, then they will mix with each other. If they are very different, they will not. And that kind of goes with people too, right? It's much easier to mingle with people that you have a lot in common with. A common language, maybe some common experiences, common interests. You're going to mix together better than with someone who doesn't speak your language and you have no common background, no interests in common. It's really hard to get along with people like that. Okay, so like dissolves like. So let's look at this concept check. Which of the following solutes will generally not dissolve in the specified solvent? And we're going to choose the best answer, assuming all the compounds are in the liquid state. So if we've got CCl4 mixed with water, now we have to think about polarity when we do this. So we have to look at this. This is carbon tetrachloride. And I would not expect it to be obvious to you just from looking at the formula. But if we draw the Lewis structure for carbon tetrachloride, we had something like this. And then, where are my electrons? There's electrons out here. Those don't really matter, but just to be thorough, I'll stick those in. So that's the Lewis structure for carbon tetrachloride. Is that molecule polar? No, it's nonpolar. Remember, we had two conditions. We look at the central atom and we ask ourselves, are there any lone pairs on the central atom? No. And then we ask ourselves, are all the atoms bonded to the central atom the same? They are the same. So this is a very symmetrical molecule, and so this is a nonpolar molecule. Oops. Nonpolar. We should know, you should just know that water is polar. So, carbon tetrachloride being nonpolar, is that going to mix with water that's polar? No. So the question's asking which will not dissolve. So that's one that will not dissolve. Let's look at the next one, NH3. Well, again, we need to look at the Lewis structure to see if it's polar or not. There's the Lewis structure for ammonia, NH3. Is that molecule polar? Does it have lone pairs on the central atom? This is the central atom. What are these dots? A lone pair. There is a lone pair on the central atom. And so this molecule is going to be lopsided. It's going to be polar. The atoms bonded to it are all the same, and that's really nice and all, but it's not symmetrical. Okay, so this is a polar molecule. Oh, again, I forgot. Polar molecule. So ammonia being polar, is that going to mix with water that's polar? Yes, because like dissolves like. Question?
What did you call the dots again?
A lone pair. Yep. So when we talked about Lewis structure, these lines are two dots that are shared, two electrons that are shared, and they form a bond. And so we usually use a line instead. And then there are electrons that are just on an individual atom, and those are lone pairs. They're not involved in bonding. So ammonia does mix with water. How about methanol? CH3OH. What's your best guess? Is that one polar or nonpolar? Polar. It's not symmetrical, is it? Over here we've got oxygen with a hydrogen on it, and over here we've got carbon with 3 hydrogens. It's not symmetrical. This one is really nice and symmetrical. Ammonia kind of looks symmetrical, but there's this lone pair here. If there was a hydrogen here, that would be different. So we're going to guess that this one, we're going to guess correctly, that this one's polar. So, polar substance mixing with polar solvent. It does dissolve. Let's look at this last one. Nitrogen gas mixing with methane. Well, this molecule is 2 nitrogen atoms bonded together. Is there any way that that could be polar? No, because the 2 atoms in that molecule are exactly the same. So why would one have more attraction for the electrons than another? It wouldn't. So this guy's nonpolar. And now we're not talking about water, we're talking about methane. I'm going to go back up to the top where I've got, well, yeah, up to the top where I've got a little room. Methane is carbon with 4 hydrogens bonded to it. What do you think, polar or nonpolar? Nonpolar. It's nice and symmetrical, just like this guy. There's no lone pairs to mess things up on the central atom. So this is a nonpolar solvent. So here, nonpolar nitrogen with nonpolar methane. Are those going to mix? Yes, they are. Like dissolves like. So nonpolar mixes with nonpolar, polar mixes with polar, but polar and nonpolar do not mix. So in A, we have a nonpolar with polar. Those don't go together. And down here, we have nonpolar and nonpolar, and those are fine together. Any questions?